Welcome to lesson 4 on power system analysis. Before we start this lesson 4, first I would like to take up the questions that we asked in lesson 3. First question was, what are the types of conductors used for overhead transmission line? Well, some of the types of conductors used for overhead transmission lines are copper conductors, which is very rarely used nowadays, ACSR, that is aluminum conductor, steel reinforced conductors, then all aluminum conductor or ACAR conductors or expanded ACSR conductors which are used. As I have already said in lesson 3, sometimes we want to increase the effective radius of the conductor, and for that we use expanded ACSR conductor in EHV transmission lines. Next question was, how does conductor diameter affect inductance of a transmission line? Well, if you remember the equation for inductance, which was L is equal to 2 into 10 to the power minus 7 log n d by r dash henries per meter. Now, from this expression it is very clear that inductance is inversely proportional to r dash or the effective radius of the conductor. So, increasing effective conductor radius will result in decreasing line inductance, and that is why, as I said earlier, sometimes we use expanded ACSR conductors for transmission lines, especially in extra high voltage transmission lines. Now, we will start our lesson 4, which will be on inductance calculations for 3-phase transmission lines. Well, in this lesson we will discuss inductance calculation for 3-phase transmission lines with equilateral spacing, then with transposition, again with when we are using bundle conductor lines, and finally lines with ground return. Well, first we will take the calculation of inductance for a 3-phase line with equilateral spacing or equal spacing. Now, here in this diagram you can see A, B, C are the 3 conductors which are placed at the vertices of a equilateral triangle, that is the distance among all 3 conductors are say, that is distance d. Now, if we calculate the flux linkage of conductor A due to currents flowing in conductor A, B and C, then it will be equal to 2 into 10 to the power minus 7 into I A log n 1 by r dash, where r dash is the effective radius of conductor A. As we have seen, the effective radius of conductor is generally lower, it is about 0.7788 times the radius of the conductor, plus I B into log n 1 by d, that is the distance of conductor B from conductor A, plus I C, the current flowing in conductor C, into log n 1 by d, again the distance between conductor C and conductor A. This is equal to 2 into 10 to the power minus 7 I A log n 1 by r dash plus I B plus I C log n 1 by d, that is we have combined these 2 terms, so we have got this. Now, we know that for a 3-phase 3 conductor line, I A plus I B plus I C is equal to 0. Therefore, I B plus I C is equal to minus I A. Therefore, we can write lambda A is equal to 2 into 10 to the power minus 7 I A log n 1 by r dash minus I A log n 1 by d, which results into 2 into 10 to the power minus 7 I A log n d by r dash Weber turn per meter. Now, once we have got the flux linkage, we can calculate the inductance very easily. L A, inductance of conductor A, is equal to lambda A by I A, which comes out to be 2 into 10 to the power minus 7 log n d by r dash henries per meter. Since all the 3 conductors are equally spaced, therefore, inductance of phase B and phase C conductors will also be same. Now, we take the inductance calculation for a 3 phase transposed line. As we have said earlier, because of physical limitations, it is not always possible to have a equilateral configuration for the conductors. So, by transposition, what we do is we try to make the flux linkage of all the 3 phase conductors more or less same. Now, what we do here is, if we have a transmission line, say from this point to this point, these 3 phase lines, what we do is we change the position of the 3 phase conductors over 1/3 of length of the line. Like if we see here, for first 1/3 length of the line, the position of conductor of phase A is in position 1, phase B is in position 2, phase C is in position 3. Now, for the next 1/3 length, what we do is the phase A conductor goes to position 2, phase B conductor goes to position 3, and phase C conductor goes to position 1. And similarly, for the next 1/3 length of the line, that is the last 1/3 length of the line, the phase A conductor now moves to position 3, phase B conductor moves to position 1, and phase C conductor moves to position 2. In this way, each phase conductor has gone through all the 3 positions for 1/3 length of the line, and therefore, the total flux linkage for each of the phase conductors will be almost same, and this, because of this, the inductance will also be on the average be same for the 3 phase conductors. This makes the transmission line more balanced. So, now let us find out the flux linkage of phase A conductor in first 1/3 position of the conductor. This is we write as lambda A 1. This is equal to 2 into 10 to the power minus 7 into I A log n 1 by d s. Here I am writing d s instead of r dash, because sometimes we use instead of one conductor more conductors. So, we are talking about the self distance, which is r dash for a single solid conductor line. So, it is I A log n 1 by d s plus I B log n 1 by d 1 2, because in this first 1/3 position, current I B is flowing in the conductor 2, and here we have the distance d 1 2. Similarly, this plus I C log n 1 by d 3 1, which is again I C is flowing in this conductor, and the distance between them is d 3 1. Similarly, for the phase A conductor in the second 1/3 length of the line will be 2 into 10 to the power minus 7 into I A log n 1 by d s, that is its own distance, plus I B log n 1 by d 2 3. If we see here, in this I B is now in this position, I A is in this position, the distance between these two is d 2 3. Plus I C log n d 1 2, again if we see I C is flowing in this and I A is flowing in this. So, distance between them is d 1 2. Similarly, for the last 1/3 portion of the line, we have the flux linkage with phase A conductor equal to 2 into 10 to the power minus 7 into I a log n 1 by d s plus I b log n 1 by d 3 1, because now I b is occupying position 1 and I a is occupying position 3, plus I c log n 1 by d 2 3, as we see here I c now is occupying this position and I a is occupying this position, this is d 2 3. Now, the total flux linkage of the conductor over the whole length can be given by sum of these multiplied by their lengths, and if we want to take the average per meter length, the flux linkage will be lambda a 1 into L by 3 plus lambda a 2 into L by 3 plus lambda a 3 into L by 3 divided by L, or the average flux linkage of phase A conductor which occupies all the 3 positions is going to be the average of lambda a 1 plus lambda a 2 plus lambda a 3 divided by 3, that is average of the lambda in all the 3 positions. This, when we substitute the values of lambda a 1, lambda a 2 and lambda a 3, comes out to be 2 into 10 to the power minus 7 divided by 3 into 3 I a log n 1 by d s plus I b log n 1 by d 1 2 into d 2 3 into d 3 1 plus I c log n 1 by d 1 2 into d 2 3 into d 3 1, which will finally turn out to be, because we can now combine these two terms I b and I c terms, because the denominator, the two terms log n terms are same. Therefore, this we can write as lambda a is equal to 2 into 10 to the power minus 7 divided by 3 into 3 I a log n 1 by d s. Now, I b plus I c is equal to minus I a. So, we can write this as minus I a log n 1 by d 1 2 plus d 2 3 plus d 3 1. Now, we can combine these two terms and then we will get 2 into 10 to the power minus 7 I a log n cube root of d 1 2 into d 2 3 into d 3 1 divided by d s, Weber turn per meter. So, the average flux linkage per meter for conductor A comes out to be this much, and as we have seen, since all the 3 phase conductors occupy all the 3 phases, so the flux average flux linkages for phase B and phase C conductors will also be same. Now, once we have got the flux linkage, average flux linkage, we can get the inductance, average inductance per meter length of the line as lambda a by I a, which turns out to be 2 into 10 to the power minus 7 log n cube root of d 1 2 d 2 3 d 3 1 divided by d s, where this term cube root of d 1 2 into d 2 3 into d 3 1 is called the equivalent distance of the 3 phase system, that is the equivalent distance between the 3 conductors. This is also seen as the GMD of the 3 phase conductors. Therefore, La is equal to, or the inductance of phase A is equal to 2 into 10 to the power minus 7 log n Deq by ds, where Deq is the GMD of the 3. Now, as we have said earlier, that in order to reduce the inductance of the transmission system, we can do this by increasing the resistance, increasing the radius of the conductor. That is, the effective radius of the conductor should be increased, and this can be done by means of bundle conductors. In fact, bundle conductors are used for 2 purposes. One is it reduces the electric field strength on conductor surface, and therefore, it reduces corona losses and radio interference and audible corona losses. All these aspects which is associated with corona get reduced. Now, how does this happen? Now, if you see, if we use a conductor with a radius r, then its volume will be pi r square. Now, if we take two conductors with the same its surface area is pi r square. If we take two conductors with the same cross sectional area, then its radius is not going to be r by 2, its radius is going to be r by root 2. Now, if we have this, then the surface area of 1 meter length of the conductor, in case we are using two conductors instead of one, will be now pi into r by root 2 multiplied by 2. So, it will be root 2 into r, whereas in the other case it will be pi r only. So, here what we see is the surface area of the conductor increases considerably, and because of this the electric stress reduces. Another effect that we get when we bundle the conductors is that it increases the effective radius or the GMR or the self distance of the conductor considerably, and this reduces the inductance, and this is one of the reasons why we use these bundle conductors. These bundle conductors are used by having more than one conductor which are supported by a conducting frame at regular intervals along the transmission line. Here you see a bundle conductor with two conductors, here this is a bundle conductor with three conductors and bundle conductor with four conductors. In fact, for very high voltage lines sometimes we use more than 4 conductors also. In India normally we are using 2 conductors or 4 conductors for 400 kV line, and 2 conductors sometimes are used for 220 kV lines. Now, if we look at the effective radius of the conductor when we are using 2 conductors which are placed at a distance d, normally this distance d is approximately 10 times the diameter of the conductor. So, here if we look at this 2 conductor configuration, a bundle with 2 conductors, then ds will be equal to, we are taking all the distances, the distance, its own distance from itself will be r dash, then its distance from this conductor will be d, then the distance of this conductor with itself will be r dash, and distance of this conductor with this will be d. So, there are 4 distances involved, and it will be 4th root of r dash into d whole square, that is r dash square into d square, which is equal to square root of r dash d, which is certainly much higher than r dash, because d is much larger than r dash. Same thing for 3 conductor, we can get 9 distances, that is 3 distance for each conductor, one its self distance and 2 for the other 2 conductors, and same thing for each one of the 3 conductors. Therefore, we get the self distance ds as 9th root of r dash into d whole cube. This is equal to cube root of r dash into d square. Similarly, when we are using 4 conductors, we have got 16 distances, 1 for itself and 3 more for the other 3 conductors, distance from this conductor to the other 3 conductors. Therefore, we get the self distance ds is equal to 16th root of r dash into d into d root 2, which is the distance between this conductor and this conductor. Same thing will happen for this conductor and this conductor, and so on. So, into to the power 4, which comes out to be 1.091 into 4th root of r dash d cube. And as we have seen earlier, the inductance we can get for these bundle conductors as L is equal to 2 into 10 to the power minus 7 log n Deq by ds, where ds is what is the GMR for the bundle conductor. Since this has increased considerably as compared to the single solid conductor having the same cross sectional area, therefore, the inductance gets reduced considerably. Now, we will take up 3-phase line with earth return. Now, this is a normal situation that the 3 conductors may be horizontally placed, and we have at the top of the transmission tower earth wires or the ground wires. These ground wires, as I have said earlier in lesson 2, that these ground wires are used to protect the phase conductors from direct lightning stroke. Now, these ground conductors are normally conducted or connected to the tower, and at each tower footing they are grounded. So, earth conductors are connected in parallel and grounded at regular intervals along the transmission line. If they are not grounded at each tower, maybe they will be grounded at every alternate tower or so. So, how do we find out the inductance for such a system? Normally, when the system is working as a balanced system, there will not be any return current flowing, because the sum of the 3 currents will be 0 all the time. But in case of unbalanced currents flowing in the system, we have some currents flowing through these return conductors, which will again go to the ground and will flow through the earth. So, if phase currents are not balanced, return currents will flow in earth conductors and ground, because since these earth conductors are connected to the tower and again they are grounded by the footing tower footing. So, the current flowing in these earth conductors will go into the ground and will disperse and flow in the ground also. Now, it was J.R. Carson in 1923 who effectively or who proposed how to take care of these ground currents in the system, in the transmission system. So, he was which was later modified, he was the first person to model these ground currents into the system. What he did was, he said that earth return conductors are basically, or the earth current can be basically represented by earth return conductors, which are having the same GMR as the overhead conductors and are located directly below the overhead conductors at a distance dE, as shown in this figure. That is, here we have 3 phase conductors A, B and C, and we have 2 earth conductors or the ground conductors, which are N1 and N2. Now, what he proposed is, for such a system, he said that the ground current flowing can be represented by conductors A dash, which is directly below A into the ground, at a distance d from that conductor. Same thing for N 1, we have a conductor N 1 dash which is in the ground or which is directly below this in the ground at a distance d, and so on, where he said dE, the distance at which these conductors are from the overhead conductors, is proportional to rho, the earth's resistivity, and inversely proportional to frequency of the system or the frequency of the current which is flowing in these conductors. So, now we can see that d for any conductor k, we have the ground conductor dk k dash, the distance of its own that is same as dk k, which is the GMR of that conductor, and the distance dk to k dash for any conductor k to k dash is dE, and the dk k dash, which is the distance of this conductor to itself, is same as the GMR of this conductor. And he said that dE is equal to 658.5 into square root of rho by f. Now, this is an empirical formula which was found after lots of experimentation, where rho is the earth's resistivity, and if one does not know the earth's resistivity properly, then one can always choose 100 ohm meter as the earth's resistivity, which is the resistivity for a wet earth. He also found out that the resistance of these image conductors or the conductors which are representing the ground current is given by R k dash is equal to 9.869 into 10 to the power minus 7 f, where f is the frequency per ohms per meter. So, these dE and R k dash are empirical values, and these have been found out after lots of experimentation. Now, for this system that we have 5 conductors here and 5 conductors as images below these conductors at a distance dE from the overhead conductors. Now, this makes a total of 10 conductors. Now, sum of the currents in all the 10 conductors will have to be equal to 0. So, in this system, sum of the current I k is equal to 0 for k is equal to 1 to 2 times into 3 phase conductors plus 2 neutral conductors, that is sum of all the 10 conductor currents is equal to 0. Now, for such a system we can find out the flux linkage for any conductor very easily, and lambda k in this case is given by 2 into 10 to the power minus 7, sigma m is equal to 1 to 3 plus 2, that is 3 phase conductors plus 2 ground conductors, I m log n d k m dash, that is distance from the conductor to the conductors which are the image conductors, divided by d k m, the distance between 2 overhead conductors, and these include the ground conductor as well. So, lambda k is 2 into 10 to the power minus 7, sigma m is equal to 1 to 5 I m log n d k m dash by d k m Weber turn per meter. Since lambda is equal to L into I, where L is the inductance and I is the current. Now, in this case, since there are 5 conductors, we have lambda for all the 5 conductors that is lambda a, lambda b, lambda c, and lambda n 1, lambda n 2. So, lambda is a 3 plus 2 vector. I again, since the current is flowing in all these 5 conductors. So, I is a 3 plus 2 vector. Now, L, which is the inductance matrix, is also a 3 plus 2 into 3 plus 2 matrix, whose elements L k m is equal to 2 into 10 to the power minus 7 log n d k m dash by d k m. This comes out from the previous relation of lambda k. So, lambda k we know. So, if we sum this up and then we find out the inductance for the conductors, then L k m will come out to be this much, and therefore, we can write this as a matrix equation where we are saying E A A is the voltage drop in phase A conductor, E B B is the voltage drop in phase B conductor, E C C is voltage drop in phase C conductor. For the neutral conductors, since they are grounded, their potential is 0. So, voltage drops are going to be 0 for the 2 ground conductors. This is equal to R plus j omega L, which will be again a 5 by 5 matrix, into I A current in phase A, I B current in phase B, I C current in phase C, I N 1 current in neutral 1, and I N 2 current in neutral 2 or ground 2. Here the matrix R is a 5 by 5 matrix, and this is represented by, for R A A, what we have is R A plus R k dash, that is, this is for R A is the resistance for conductor A, plus R k dash is the resistance for the image conductor, which is below A. Then we have R k dash for the other 4. Similarly, for R will be R 1 2 will be R k dash, R 2 will be R b plus R k dash, R 2 3 will be R k dash, and so on. So, this is a 5 by 5 matrix which gives resistance in ohms per meter for this 5 conductor system. Now, if you write the complete system equation for the voltages across the line conductors, then we will have the voltages E A A, E B B, E C C, that is the voltage across the 2 points of the phase A conductor, phase B conductor, and phase C conductors. Similarly, for the neutral conductors, since the neutral conductors are grounded, these voltages will be 0. This voltage is going to be equal to the impedance multiplied by the current, which gives the voltage drop across the 2 points. Now, here the impedances will be Z 11, Z 12, Z 13, Z 14, Z 15. All these impedances will be, this will give a 5 by 5 matrix, and the currents will be the 3 phase currents I A, I B, I C, I N 1 the current in neutral conductor 1, and I N 2 in the neutral conductor 2. So, this for this 5 conductor system, we have 5 set of equations, and the impedance matrix is a 5 by 5 matrix, which we can divide into 4 different submatrices as shown here. Z A, which is a 3 by 3 matrix, which indicates the Z 11, Z 12, Z 13, Z 21, Z 22, Z 23, Z 31, Z 32, Z 33. These impedances are relating the voltages across the phase conductors with the currents flowing in the phase conductors. Similarly, the voltages across the phase conductors due to currents flowing in the neutrals can be given by the impedances shown in this ZB, that is Z14, Z15, Z24, Z25, Z34, Z35, and Zc indicates the voltage across the neutral conductors due to currents in the phase conductors. These impedances are Z41, Z42, Z43, Z51, Z52, Z53. Similarly, for the voltage in across the neutral conductors due to currents in the neutral conductors will be given by this matrix Zd, which is Z44, Z45, Z54, Z55. So, we have 3 submatrices Za, which is a 3 by 3, Zb, which is a 3 by 2 matrix, Zc, which is a 2 by 3 matrix, and Zd, which is a 2 by 2 matrix. This is the complete system equation that we have, where the impedance terms are given as for the diagonal elements, that is Zkk, which means Z11, Z22 and so on, are given by Rk plus Rk dash plus j omega 2 into 10 to the power minus 7 log n dkk dash by dkk ohms per meter, whereas these are the distances as we have seen in the system diagram earlier. The off diagonal elements, that is Zkm, which is basically Z12, Z13 or Z54, all these off diagonal elements, that is when k is not equal to m, is given by Rk dash plus j omega into 2 into 10 to the power minus 7 log n dk m dash by dk m ohms per meter. So, we can compute all these diagonal and off diagonal elements, that is the elements of this impedance matrix, using these relationships. Now, what we can do, since we have already divided this system into 4 submatrices, now we can write this whole system of equation in a short form like EP, where EP is the voltage drop across the phase conductors, 0 is the voltage drop across the neutral conductors. This is equal to Za, Zb, Zc, Zt into Ip, where Ip is the current flowing through the phase conductors and In is the vector of current flowing through the neutral conductors. As shown here, Ep is equal to Eaa, Ebb and Ecc are 3 phase conductor voltage drops. Ip is equal to the phase currents Ia, Ib, Ic, and In is the current flowing through the 2 neutrals In1, In2. Now, from this set of equations, we can write this into 2 separate sets of equation as Ep is equal to Za Ip plus Zb In. Ep is equal to Za Ip plus Zb into In. Similarly, 0 is equal to Zc into Ip plus Zd into In. 0 is equal to Zc into Ip plus Zd into In. Now, from this second equation, we can take this term this term on the other side, then we have In is equal to minus Zd inverse Zc into Ip. That is, In is here and we have taken this on this side. So, it is minus Zc Ip. Now, we pre multiply both sides by Zd inverse. So, we will get In is equal to minus Zd inverse Zc into Ip, and therefore, putting for this In here in the first equation, we will get Ep is equal to Za into Ip minus, because this minus term is coming, Zb into In. So, In is given by this relationship. So, minus Zb into Zc into Zd, sorry, Zb into Zd inverse into Zc Ip. So, we have substituted for In from here, and then we are writing this expression like this. Now, we can write this whole as Ep is equal to Zp into Ip, where Zp is this matrix here. This will be a 3 by 3 matrix. Zp is equal to Za minus Zb, Zd inverse Zc. So, this is what we will get, that is, we have eliminated in this equation the current In, and we are writing all the equations in terms of the phase variable. Only thing is, this is taken care by using Zd inverse and Zc from this expression. Therefore, we will get now Z p, which will be a 3 by 3 matrix as Z A A, Z A B, Z A C, Z A B or Z B A will be same, Z B B, Z B C and Z A C, Z B C, Z C C. So, this is now a 3 by 3 matrix from where we have eliminated the currents in the neutral conductors or the ground conductors. So, here we are getting a relationship only for the phase conductors, E p is equal to Z p into I p. So, the currents flowing in the ground conductors or the ground is now eliminated, and we can now get a relationship only for the conductors currents in the phase conductors relating the voltage drop in the phase conductors. Now, for a fully transposed line, what we will have is, since these phase conductors will be occupying all the 3 positions for 1/3 length of the line, therefore, we will get the average values for all the 3 flux linkages and the inductances, and therefore, we will have the same impedance for all the 3 phases. So, self impedance Z A A will be same as Z B B, will be same as Z C C, that is all the 3 phases will have the same self impedances, and the mutual impedances will also be equal for all the 3 phases. So, Z A B and Z A C will be equal, which will be also equal to Z B C and Z C A. So, we get finally for a fully transposed line, we get the values or the impedance series impedance matrix for the 3 phase system with ground return as Z p is equal to Z A A, Z A B, Z A B, Z A B, Z A A, Z A B, Z A B, Z A B, Z A A. This matrix will give me the impedance, series impedance of the transmission line with ground return. So, Z A A is equal to, as I said, the average value, and Z A B will be also equal to the average value, the mutual and the self will be given by these 2 relationships. Now, let us take an example for finding out the inductance of a 3 phase transmission system. The example that we are taking is for the conductor configuration of a completely transposed 3 phase overhead transmission line with bundle conductor is shown. All the conductors have a radius of 0.74 centimeter with a 30 centimeter bundle spacing. That is, we have a 30 centimeter bundle spacing for the conductors, and each conductor has a radius of 0.74 centimeter. The distance between the 2 phase conductors is 6 meters, that is from center to centers, and this is a horizontally spaced configuration. The line is fully transposed. For this line, determine the inductance per phase in millihenry per kilometer and in millihenry per meter. Find the inductive line reactance per phase in ohms per meter at 50 hertz. So, this is the question that we will have to find out the inductance per phase of the line in millihenry per kilometer and millihenry per meter. We will also need to find out the inductive line reactance per phase in ohms per meter at 50 hertz. So, for this system, what we have to do is we have to find out the equivalent distances. So, for the given configuration as shown in figure, we have the mutual GMD between the different phases given by DAB is equal to R 13 R 14 R 23 R 24, that is distance from here to this conductor, distance from this to this conductor, distance from this to this conductor, distance from this to this conductor, and fourth root of that, because again if we take the distances from this to this and this to this, this to this and this to this, that will also be same. So, it will be the fourth root of DAB is the fourth root of distance between 13, 14, 23, 24. So, this is equal to 6 into 6.3 into 5.7 into 6, that is 13 is 6, 23 is 5.7, 14 is 6 plus 30 centimeters. So, 6.3 and 24 is 6. So, we take the fourth root, it comes out to be 5.9962, it is same as almost 6 meters. Similarly, for between B and C, if we do this, we will get the same distance or the same GMD. But for DCA, if we look at this between C and A, then we have the distances 1 to 5, 1 to 6, 2 to 5 and 2 to 6. Therefore, DCA is equal to R15 into R16 into R25 into R26, the fourth root of this, that is equal to 12 into 12.3 into 11.7 into 12, fourth root of that is 11.9981, which is very near to 12 meter. Now, the equivalent equilateral spacing between the phases is given by DEQ, defined as DEQ is equal to DAB into DBC into DCA, cube root of that. So, if we find out the equivalent equilateral spacing DEQ, that comes out to be 5.9962 into 5.9962 into 11.9981, cube root of that, that comes out to be 7.5559 meter. Now, the self GMD of all the three phases owing to symmetry are equal, that is the self distance, each conductor has the same radius and the distance between the two conductors of a bundle is same, that is 30 centimeter. So, therefore, the ds for each phase conductor is going to be equal to r dash, that is 0.7788 into r for the conductor into 30 centimeter, which is the distance between the two conductors of the same bundle. The square root of this comes out to be 4.1580 centimeter. In fact, we could have taken all the 4 distances, as we have seen earlier, ds is r dash into d, square root of that. So, this is equal to 4.1580 centimeter. Now, you see this is much larger than 2 times of 0.7788 into r, which is 0.74 centimeter. Therefore, bundling has increased the effective radius considerably. Therefore, now we can find out inductance per phase for the given system as L is equal to 2 into 10 to the power minus 7 into log n DEQ by ds henries per meter per phase, which is equal to 1.04049 into 10 to the power minus 6 henries per meter per phase, which can be written as 1.04049 into 10 to the power minus 3 millihenry per meter per phase, or 1.04049 millihenry per kilometer per phase. The inductive line reactance per phase at 50 hertz is given by x is equal to 2 pi f into the inductance. So, this is 2 pi into 50 into 1.04049 into 10 to the power minus 6 ohms per meter per phase. This comes out to be 3.270 into 10 to the power minus 4 ohms per meter per phase. So, this is how we can calculate the inductance and the inductive reactance for any given 3-phase transmission system. Now, before we finish, I would like you to answer the following questions. First is, why bundle conductors are used in EHV lines? Second question is, what is transposition? And third question is, how the effect of earth return current is taken into account in inductance calculation for a 3-phase line with ground return system, especially when the system is carrying unbalanced current. So, with this we finish this lesson. Thank you very much. We will meet again for lesson 5, in which we will talk about calculating the capacitance of the transmission line. Thank you. Well, welcome to lesson 5 on power system analysis course. In this course, we will talk about the transmission line capacitance. Before we get into the calculation of transmission line capacitance, I would like to answer those questions that I asked in lesson 4. The first question was, why bundle conductors are used in EHV lines? Well, the answer to this question is bundling of conductors, that is, instead of using one single conductor, use of a number of conductor connected by conducting frames reduces electric field strength on conductor surface, which in effect reduces the corona losses, which result in power loss as well as radio interference and audible noise in the system. Bundling also increases the effective radius of the conductor and thereby reduces the inductance of the transmission line. This in effect will improve the regulation of the transmission line. As seen from here, the effective radius for a 3-conductor bundle, which are spaced at a distance d from the center, or d from each other with a radius r, is given by 9th root of r dash into d whole cube, which is equal to cube root of r dash d square. This is much larger than r dash, which is used when a single conductor is used, and therefore bundling helps in reducing the inductance as it increases the effective radius. Therefore, we will take the case of a 3-phase system. We will start with the 3-phase line with equilateral spacing, because as we have seen for inductance calculation, we can always convert, if the line is transposed, we can always convert any system into an equivalent 3-phase equivalent equilateral spacing of the conductors by finding out the equivalent distance DEQ. So, here we have a equilateral spacing, conductor A, B and C each with a distance d from each other. We also assume that this system consists of only 3 conductors. So, the sum of the total charges will be equal to 0, that is q A plus q B plus q C is equal to 0. So, for solving this, we will take case of a fully transposed 3 phase line. So, we have the fully transposed 3 phase line. The voltage is given by the relationship VAB is equal to 1 by twice pi epsilon, I am sorry, this is epsilon into QA into log n DEQ by R plus QB into log n R by DEQ, where DEQ is equal to D12 into D23 into D31 to the power 1 by 3, that is cube root of D12 D23 into D31. Now, substituting these values, we get this as equal to 12 meters into 12 meters into 24 meters, that is the distance between the conductor A and C. The cube root of this will give us equal to 15.119 meter. Similarly, we can write the relationship for VAC, and VAC will be equal to 1 by twice pi epsilon into QA into log n DEQ by R plus QC into log n R by DEQ. Calculate these quantities for a transmission system. So, this example we have a 3 phase 400 kV 50 hertz 350 kilometer overhead transmission line that has a flat horizontal spacing with 3 identical conductors. That is, we have 3 identical conductors placed in a flat horizontal spacing. The conductors have an outside diameter of 3.28 centimeter, that is, the diameter of the conductor is 3.28 centimeter, and the distance between the adjacent conductors is 12 meter. Now, for this system, determine the capacitive reactance to neutral in ohms per meter per phase and the capacitive reactance for the line in ohms per phase. Thank you.